Stress and strain diagrams are pretty simple to understand. They are graphical representations of results from a tensile test. We are referring always to the stress in a particular cross-section, and when we compare it to the strain of the specimen or percent change. Important parts to look out for in these graphs are modulus of elasticities, yield stress or point, ultimate stress or point, rupture stress or point, the modulus of resilience, and the modulus of toughness. Sometimes we can't find the yield stress or point very easily because it is when the graph is no longer linear. And in the cases for very ductile materials, this is very hard to distinguish. So often what we will do is we will create an offset line to help us approximate what the yield stress will be. This is an example of a stress-strain diagram. Let's go over the important points that I previously mentioned. The yield stress is where the graph stops being linear and starts looking more curvy. The ultimate stress is the absolute maximum stress that the material will achieve before failure. Rupture stress is the stress that the material will fail at. The modulus of toughness is the area under the curve. We obviously can't integrate this by conventional means, so you will have to approximate the area under the curve. I usually divide the shape into several shapes and find the area of those shapes and add them together like this. Now we will take the same curve and look at the magnified region of it, specifically the linear region. To find the modulus of elasticity, all we need to do is find the slope of this region. This is best done by taking rise over run, going from one point to another. Then to find the modulus of resilience, you need to take the area under this linear region. I think this is best done by treating it as a triangle from the yield stress to the beginning and doing base times height over 2. To help clarify what I stated earlier about the offset rule, let's look at this graph. You probably can find most of the previous points found on the graph as well, but where would the yield stress be? When we zoom in on the linear region, we see that there isn't much of a defined point. So what we do is draw a line that is 0.2% from the beginning, which means 0.002 strain, and draw it until it intersects with the graph, using the same slope as the modulus of elasticity. Then we define the yield stress as that point. Therefore, our yield stress would be about here. A good point about finding this yield stress is then we can, of course, know when that ductile material has been plastically deformed.